This experimental rig provides a flow of air through the Perspex tube. And this probe is an airflow meter. It gives an output signal dependent on airflow. Now, why should I be looking at this particular measurand? Well, the reason is that the airflow is turbulent. And because turbulence is a random process, we obtain a signal that varies in a random fashion. In case you're wondering, the probe I'm using is a hot wire anemometer. The essential part is a heated element here. It's open to the air, and it's held at a constant temperature by an electric current flowing through it. The moving air has a cooling effect. The faster the air, the more heat it takes away from the element. And the current required to hold the element at its fixed temperature is used as a measure of airflow. Now, I don't particularly want to talk about flow meters, but I do want to talk about random signals in preparation for your signal processing lab. There's nothing particularly unique about a signal like this. As a rule, all signals of interest exhibit some degree of random behavior. But it's necessary to know how to handle random signals if you're going to design, or at least understand, the design of practical instrumentation systems. And that's why you spend a whole lab session looking at random signals here at summer school. But before you start on your practical work, I want to show you one or two things about modeling signals like this mathematically. The first point to note is that the general level of the signal depends on the average airflow. If I reduce the airflow, you see that the signal level is reduced, and it's restored again when I take my hand away. Now, as long as conditions in the system remain constant, then the average position of the signal will also remain constant. But of course, the most notable characteristic is the random variation. In some cases, we see fluctuations like these caused by noise and interference on the transmission path. But we know in this case that the fluctuations are due to turbulence in the airstream, and as such, they're a real feature of the signal. So you can think of the signal as being made of two parts. There's a steady average value, which is a measure of the average airflow, with a random component superimposed upon it. Now, the random signals differ from so-called deterministic signals, like sine waves or square waves, in that their precise value cannot be predicted in advance. There are no mathematical equations for a random signal that will allow you to predict precisely what will happen in the future. Nevertheless, there's often a lot we can say about random signals, especially when we have a record of their past behavior. Now, this chart recorder has been plotting the output of the flow meter for the last few minutes, and you can see we've got a pretty good record here. This here is where I put my hand over the tube just now, and you can see how the signal level dropped and then came back again. Now, while this record shows how the signal has behaved in the past, the paper in here, behind the pen, represents the future. And that's often what we're interested in. We know we can't predict precisely where the pen will write in the future, but because we have this record of the past behavior, we can make some good guesses as to what the signal is likely to do or not to do. For example, provided that conditions within the air system remain constant, we can be reasonably sure that the signal will continue to fluctuate about its mean value here. Also, assuming that the signal is, so to speak, well behaved, we would expect the overall fluctuation to remain within the same broad limits as before, from here out to here, say. And from what we've seen so far, we would be very surprised if the signal were to jump suddenly and then back again. We would say that such an event was improbable, or alternatively, that there's a low probability of it occurring. And it's the use of words like probability that gives the clue to the method of modeling random signals. We may not be able to predict precisely what a random signal will do in the future, but we can do the next best thing, and that's to give the likelihood or probability of it doing something. This portion of signal is rather like the one from the flow meter, and I've added a set of axes and shown how the signal, x volts, varied with time over the observation interval. Now, we've already seen the significance of the average value of a signal, and one of the first things you'll be doing in the lab is estimating the average, or more correctly, the mean value of a random signal. Now, you'll find with practice, you'll be able to make a surprisingly good estimate of the mean value by eye, working just from an oscilloscope trace. Now, here you'll notice that the signal is everywhere positive, which suggests that the mean value is likely to be positive. And I guess that if we take into the whole signal, then the mean value is round about here. Now, I wasn't far off. This is the actual mean, and you see we use the notation x bar, and we measure it upwards here from 0 volts. We can think of the mean value as the value which effectively splits the signal into two, so that the area contained by the signal and the dotted line above the dotted line is equal to the area contained below the dotted line. And for most random signals that you'll be meeting in practice, it's also the value where at any instant we have equal chances of finding signal values above the mean value or below the mean value. It's rather like tossing a coin, where we have an equal probability, a half, of it turning up heads or tails. That's a tails. So we know there's usually equal probability of the signal being above or below the mean value. But the statistical approach to modeling goes on to ask what the probability might be of finding future values of the signal within a range of voltages, like this one here, for example. Now, past behavior tells us that the signal has spent a relatively high proportion of its time within this voltage range. So the probability that it will continue to do so in the future is fairly high. In contrast, if we consider a range of signal values up here, well away from the mean, then we see that the signal has spent a very small proportion of its time within it. And we can conclude that in future, there'll be a relatively low probability of finding values of the signal in this voltage range. But to be of any use, we've got to be able to put numbers on these probabilities. And that's what we can do using a very important curve. It's called the probability density curve. And this is a probability density curve. You see now we've got x plotted horizontally in units of volts, and this quantity here, probability density, is plotted vertically in units of volts to the -1. So what does it mean, and how can we use it to put figures on those probabilities we were looking at earlier? Well, it's like this. I need to marry up this curve with our original signal. And to do this, I have to flip over the curve and line it up so that the two axes run in the same direction, with x increasing and with the 0 points lined up. And the first thing we notice is that the peak of the distribution lines up with the mean value of the signal. But what about precise values of probability? Well, if we look at a small range of values as before, then the probability of finding signal values within this range at any instant is simply the area under the curve as defined by the range. Likewise, if we look at a different range of values, then the probability of finding the signal in this range is given by this area. And this reflects our earlier observation. Where the probability of finding the signal is small, we have a small area. And where the probability is larger, we have a correspondingly larger area. So the probability of the signal having a value in this range is given by measuring this area under the curve. This range has a particular significance, which I'll come to in a moment. But notice, because this curve extends all the way up to plus infinity and all the way down to minus infinity, and because the signal value must lie somewhere on this axis, then the probability of finding the signal between plus and minus infinity is 1. So the total area under the curve, measured over the whole axis, must also be equal to 1. Also, this type of bell-shaped curve is typical of many random signals that obey so-called Gaussian statistics, and it's called a Gaussian curve. You'll find on the course that the curve is very precisely specified, and that we can use tables to look up the probabilities of finding voltages in different ranges. But what's so special about this range here? Well, it's symmetrical about the mean, and it extends sigma volts to either side of it. And sigma is a constant of the Gaussian curve. It's called the standard deviation. It's an important signal parameter because it tells us how much a signal deviates or varies from its mean value. If we get large excursions in a signal to either side of the mean, then the standard deviation will be large, and this will lead to a relatively wide density curve. If, on the other hand, the signal varies by only a small amount, the standard deviation will be small, and the probability density curve will be correspondingly narrower. But whether we have a broad or a narrow curve, the total area underneath it must always be 1. Now, it so happens that the area here is 0.68, which means that at any instant there's a 68% probability of the signal having a value in this range. If we go to 2 standard deviations to either side of the mean, then the area enclosed under the curve becomes 0.95, which means there's a 95% probability that the signal will lie within this range to within 2 standard deviations. And there's a 99.5% probability that the signal will be within 3 standard deviations from the mean. So for all practical purposes, we can suppose that the entire signal lies within 4 or 5 deviations from the mean value. The probability of signal values lying beyond this range is negligibly small. Not 0, but negligibly small. Now, when you get into the lab, you'll be working with equipment like this. You'll be using a random signal generator, and you'll be measuring the characteristics of that signal. There won't be time for you to develop its full probability density curve experimentally, but you will be able to develop a related curve. It's called the cumulative distribution. To see how it relates to what we already know, we'll start from the probability density curve the right way up now and work towards the cumulative distribution. Now, we know that this area gives the probability of finding the signal between these values. If this lower value becomes minus infinity, then this area gives the probability of the signal level being equal to or less than this voltage, which I'll call VR. I can represent that probability by this notation. It's the probability that X will be less than or equal to VR. And as I say, it's given by this area. Now, the cumulative distribution curve is a plot showing how P varies as VR varies. And it's like this. We plot P, the cumulative probability, against VR. For each value of VR, we plot the corresponding value of P as given by the area under the bottom curve. As VR gets larger, so the area to the left of it gets larger, and so P, the cumulative probability, gets larger. When VR reaches the mean value, half the bottom curve lies to the left of VR, so P equals 0.5. As VR moves on to higher values, so P becomes increasingly closer to 1. So you can see that this is just another way of looking at the probability density of a signal. And between now and you measuring this practically in the laboratory, you might like to think how you could find the mean value and standard deviation from a curve like this.